Oh, hello students, welcome to my 101 astronomy class where I'll be teaching you the basics of astronomy so you can continue on your journey of becoming a astronomist. Well, firstly, what is the celestial equator? Oh, let's imagine that this person is the Earth and he expands to the size of this ball, right? And if you look at the axis of the rotation, which is around here, and if you draw an equator around a circumference around the equator, you'll get the celestial equator.
This is the thick line, right?
Yep, this thick line around the ball here.
Okay.
And now, secondly, what is the ecliptic? Well, the Earth orbits around the Sun, and let's just say that this guy here is inside the ball, is the Earth, and my fist is the Sun. And if it revolves around, imagine if the Earth is the center of the orbit, and the Sun revolves around like this. If you draw the orbit of the Sun on the Earth on the ball, you'll get this line, which is the ecliptic, right here.
Yeah.
Now, these next few keywords are stuff that you should remember. Firstly, is the equinox. The equinox is when the trajectory of the Sun intersects with the celestial equator, which is this point here and this point here, right?
Yeah.
And this point is called the vernal equinox, and the other side is called the autumnal equinox. What about the solstices? Well, if you put the ball like this, the highest part of the Sun's orbit, which is here, is called the summer solstice, and the other part, where the Sun is the lowest, is called the winter solstice. And how is the daytime and nighttime different for each season? Well, during the summer, which is when the Sun is like this relative to the Earth, the northern hemisphere, the daytime is much longer than the nighttime, whereas the southern hemisphere gets much less daytime compared to nighttime, and vice versa for winter, which the Earth will be like this compared to the Sun. Now, how does the sun rise and set in each season? Well, in normal circumstances, if we take the position of the observer, which is to be the line here, the Sun would revolve along the celestial equator, which is this line right here. But when it starts getting closer to summer, the Sun will revolve closer to the summer solstice, which is here, so it will revolve around like this. The sun will set and rise like this. But if it's winter, the sun will set and rise closer to the winter solstice, which is here. Now, what I've just said previously was for the northern hemisphere. If it was for the southern hemisphere, everything I just said will be reversed.
So let's now talk about the reference point of this equatorial coordinate system. So what you see in here, this thick line over here is the celestial equator from perpendicular to the north celestial pole and south celestial pole, and the declination is the angle from, consider that you're in the center of the model, and this one is 0 declination, and you can rise up to be 90 declination north, and this one is 90 declination south, and in between is like 45 north declination and 45 south declination. One number is not enough to represent this coordinate system. You need another one, which is called the right ascension. So right ascension, I need to move the model. Please focus on the vernal equinox right here. So this vernal equinox will give it a value of 0 hour. So basically, this whole celestial equator over here is 24 hours in total, and we're gonna start with vernal equinox 0 hours, and then we're gonna move through to the summer solstice, which is follow the right hand rule, and this one will be 6 hours, and the other side will be 12 hours, and this one will be 18 hours and 24 hours and back to 0 hours. So right now with these two values, we can represent all the coordinate in this model, and the reference point would be the celestial plane, celestial plane which is on the celestial equator, and the vernal equinox for the right ascension. Yes. Now let's look at some examples, so this will not be boring. So now is the fun time. This one is equatorial coordinate system, right? And we also learn with horizontal coordinate system, which is that based on the observer. And what we want to do now is we want to convert the horizontal coordinate system into the equatorial coordinate system, but we're gonna focus on only declination. So let's imagine you are this soldier observer pointing your guns into the north, as you see over here, and you see a star, maybe right here in the north, near the north direction, and I will give it that this angle here is 60 degrees, about 60 degrees, and now this one is called the altitude of 60 degrees in the horizontal coordinate system. But what if it equatorial coordinate system? How would you transform the altitude of 60 degrees to a declination? So based on this model, you can see that the declination has a starting point, reference point of the equatorial celestial equator, right? And you can see that it moved up here. And basically, you know that assuming we are in Kevis, right? So the NCP to this one is like the celestial plane, from the horizontal coordinate system is about 50 degrees, right? And with this one is 60 degrees. So basically between the NCP and the stars is 45 degrees, right? And since this one is 45, 45 degrees, and this whole one is 90 degrees, so we know that this declination of the star is also 45 degrees. But things took an unexpected turn if we consider that the star over here is in the north, right? Is between anywhere between east to west in the north side. But if it changed to the south, the another side, to the southern side instead, the calculation is gonna be quite differently. But I'm gonna give you another example. So let's imagine that the altitude to the south, this one is from the south direction, is about 30 degrees. So this one here is 30 degrees, and basically we see again that this one is south celestial pole, right? It's over here, and since we in Kevis, so it's about 50 degrees from the plane, celestial plane. And you can see that if you add them together, 50 degrees with 30 degrees, so it's 45 degrees, right? And from the celestial equator to the SCP is 90 degrees, right? And this one SCP to the stars is 45 degrees over here, and so this one will also be 45 degrees as well. So you can also give an example that how you can convert the stars in the horizontal coordinate system based on the observer into the equatorial coordinate system with declination. Now, Professor Tan, do you know what is the definition of circumpolar star?
Sir, no, sir.
Oh no, the professor cannot know the answer, but don't worry, I'm as the assistant. I can show you what it means to be a circumpolar star. So circumpolar star is a star that you can see all year long. No matter what season it is, like what month it is, it will be in the sky every time. Maybe you cannot see it always because of the sun, but it will be in the horizontal coordinate system that you can see them. So how can we decide which star is a circumpolar star? So actually we have it depends on the latitude that you are in. For example, if you are on the 0 latitude, which is like Singapore or something like that, it will be different from when you be at North Pole. So for example, if your altitude is 0 when you are at Singapore, basically the NCP will be, like assuming you are in the sky, the NCP will be on the altitude of 0 basically. Since everything rotates around NCP, right? Since the NCP is at 0, that means that the only star that will stay in the sky will also need to have an altitude of 0, which is like a Polaris, right? But change if we go up into higher latitude, like in Thailand, 50 degrees, the NCP gonna move here about 50 degrees, and now we can have a star that circulate around here and here. So that means that the star between this one and this one, 50 degrees each, will be the circumpolar star. Now this one is based on the horizontal coordinate system, and what if we change it to a horizontal coordinate system with declination? We have a formula for that. So since this one is SCP, right, and this one is celestial equator, we know that the declination is the angle between celestial equator to NCP, right? This one is 0, this one is 90. And to be a circumpolar star, your declination must be greater than 90 degrees minus your latitude. So for example, in Singapore, latitude is 0, so your declination must be greater than 90. So you must, the star must be here, right? Exactly here. But for example, in Thailand, 50 degrees, that means that the angle must be greater than 75, right? No, yeah, 75. So that means that the declination can be around here, and since it will rotate around NCP, it can always stay in the sky. And if you're in North Pole, that means that the star anywhere will be, the declination from 0 to 90 will be in the sky, because if you're in the North Pole, NCP will be at your head and the star will circulate like here, so it will also be a circumpolar star. So this it is circumpolar star. Now we have finished our course, and as you can see, this model looks like simple, but actually it takes about an hour and a half to make this model. So please, I hope this video will benefits you into understanding the equatorial coordinate system, and with this model that we have made, I hope you can be loved with the astronomy. Thank you.